Number 9 says, for a sample size n equal to 80. So we're taking a size of 80, so that's larger than 30. That's larger than 30 is going to be real important on this next chapter. It's got to be larger than 30 for stuff to work. Find the probability of the sample mean being less than 24.3. So we want the probability that x bar is less than 24.3. And they're telling us that mu equals 24 for, so the sample, or the mean of the population is 24 and the standard deviation of the population is 1.25. So if I remember, I think where a lot of you messed up on this one is you forgot to do the very first thing. What's the mean of the sample? Same as that. And this is where it messed you up. Standard deviation of the sample means, or the
1.25 divided by the square root of 80.
you got to take, remember it's the standard deviation of the population divided by square root of n. We're going to use this formula again today, so that's part of what you're going to learn today. This time n was 80. Somebody do that for me real quick. Point what? 9. Then once we have all that, we're just going to put stuff in our calculator. Remember, in your calculator you want the low limit, high limit, your mean, mean of the sample means, and your, what was that called, the standard error, is that right? Instead of standard deviation. So what do I put in? Be careful here. What do you put in as your low limit if you want everything less than 24.3? Negative 10,000. Some of you again switch these around, messed them up. High is 24.3. Means same as the population, that's 24. This is 0.139. Punch all that into your calculator, what do you get? And again, if you draw this, it's going to help you look at stuff. If you draw before anybody tells me the answer. If I draw my normal curve here, and I know my mean is at 24, and we're at 20, we're looking at stuff less than 24.3, even without knowing all the rest of the stuff, even without using our standard error here, which is very, very small, so these numbers across through here are going to be very, very small. We should know if we're above 24, if we're at 24.3, we should know that at least what percentage of the data is going to be below that. More than 50, right? So it should be more than 50, even to get just a ballpark estimate. What'd you come up with?
0.9845.
And what happens here is, since this standard error is so small, it only goes up by like 0.1 each time. So we're at 24, then we're going to be at 24.1, 24.2, 24.3 as we go out. So we're going to be almost 3 standard deviations away from the mean. Well, we know that almost all the data should fall less than that. And with this chapter, the key idea in this chapter is to remember that we're not, for this last chapter, chapter 6, we're not looking at just the normal curve. We're looking at, if we take a bunch of different samples, how close are we going to get to that mean? That's what we were looking at. So everything was based off of that. We're taking samples and we're finding their means, and we're saying, okay, if we take a sample of 80, whatever this sample is, how likely is it that we're gonna get close to 24? If we take a sample of 100, we should even get closer to that population mean. If we take a sample of 1,000, we should get even closer and closer and closer. So all the time, our normal curve is getting steeper and steeper and steeper, and we're getting to where everything, all the data is gonna be getting closer and closer to that mean of the population. What's gonna be different on this next chapter is, when you're doing stuff like this, chapter 6 was great as far as saying, hey, we're getting closer, we should always be getting closer and closer to that population mean every time that we take a sample. The bad thing is, most of the time, we're not gonna know the population mean. There's no way that we can go out in the real world and survey everybody and find the population mean, then start dealing with little samples. And it wouldn't make sense to survey everybody and then say, okay, I want to just pick the 5 of you and see how close you are to that. We already know the population mean. Why in the world would we want to do that? So this next chapter is actually more useful because it talks about if we don't know the population mean, how sure are we that we're getting close to it? That's your answer for number 9. Again, thing that most of you probably, I think that most of you messed up. Finding that right there, you probably use 1.25 as your standard deviation instead of 0.139. Next question.
7A.
7A. Time spent in days waiting for a heart transplant for people ages 35 to 49 in recent years can be approximated by a normal distribution where the mean is 262 days and the standard deviation. So the mean's 262. Now something like this, we could actually find the mean. How many heart transplants do you think there are in the United States each year? Probably not a whole lot, right? So you can find all those people over the last 10 years and use them as a population, saying, okay, this guy waited this many days, this woman waited this many days, and you could find the actual mean of those and say that that's your population. Standard deviation is 15.8. What is the waiting time that represents the 20th percentile? 20th percentile. Remember, that can also be written P with the little 20. When we're looking at that, if we're on our normal curve, what percent of the data do we want to the left of where we're looking at? What's that 20th percentile tell us? What percent of the data has to be down this way? 20%, which is a decimal is 0.20 or 0.2. So we're looking for that. So that's the area we're looking for, the 0.2. 0.2 of the data is down this way. So on this, we know the area. We're trying to find that score right there. And it's actually, instead of a z-score this time, it's a raw score. We're trying to find that raw score, trying to find out how many days is it going to take for this person, if they're at that 20th percentile, how many days did they have to wait to get their transplant? So in our calculator, if we're looking for a z-score, we just put in area. But when we're looking for a raw score, we put in area and what else? Same for all the other stuff that we did. You put in what other two things when you're looking at raw scores? Mean and standard deviation. Mean and standard deviation. What do we put in for the area this time? .20. What's our mean? What's our standard deviation? Now this one, gotta remember that for this one, we're not looking for the area. Whenever we use the second vars, normal CDF, that's when we're looking for the area, the percent, the probability. This time we already know the probability, or the area, so this time we're using inverse norm. We're doing it backwards. If you punch that into your calculator, what do you get? 248 point what? Remember what you're looking at here. We're saying that this person, this guy right here, is waiting for his heart transplant, and he's at the 20th percentile. How many days are we expecting that he's going to have to wait? About how many? About 248, 249 days. So they're going to have to wait about 249 days. Next question.
Number 10.
10.
Even though you told me how to do this, I still need to see it.
U.S. survey of adults, 93% use the internet, so this is a binomial one. If it's binomial, we have to remember that how do we find mu for a binomial? How do you find the mean for a binomial? N times P. How do we find the standard deviation? N times P times Q. Yep. And that's what this does. It allows us to change it from a binomial into the normal setup, the normal curve, so that we don't have to go back to that binomial stuff and do all that extra work. Now there is one extra thing that we have to do, and that's we have to change it so that it makes sense on the normal curve. Part A, they want the probability that X bar equals 80. And where we got to change it at is we got to look at, since we're going continuous, again, if we were looking at the binomial, we'd be looking at whatever our mean is. We could find the mean, and we will here in a second. Whatever the mean is, then we'd be adding up all the bars from one side or the other. And I keep making this where I got like 7 or 8 bars. These actually have, if we're looking at 80, there's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up through, whatever the other side limit is. We don't want to have to add up all those bars, find the area of each bar and add them all up and do all that. So that's why we change it to the normal curve, so the calculator can just do it all for us. We got to change this though, because now when we're looking at the normal curve, if we were looking at 80 right here, let's say 80 is right here, right in the middle of that bar, well, that doesn't set well with on this normal curve, because we actually have to go down to, these are whole numbers as a binomial, because we're not going to get a person that says, if we're doing a yes or no question, we're not going to get half a person that says, I'm half yes, half no. Doesn't work that way. So we're either at 80 or we're at 81 or 82. But on the normal curve, it's continuous. So it doesn't just look at separations like 80, 81, 82, 83. So it's got to start back over here somewhere. Yes? 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 Sure. They want you in the office, Malachi. Does it take your keys with you? So we gotta change this, and we're looking at from, we want equal to 80, so we're looking at from here up to there. Well, if we said that the way we're gonna fix that is by going down by a half or going up by a half. In this case, we're gonna do both. I shouldn't have put X right there. So what's our low limit this time? If we go down by a half? 79.5. What's our high limit? 80.5. Then the other thing we still have to do, we have to find the mean and the standard deviation. They told us that 93%, so that's our P, 0.93. Our N, how many were we sampling? 100. What's 100 times 0.93? 93. And then somebody do this for me. We got 100 times 0.93 times, if P is 0.93, what's Q? 0.07. Say it again. 2.551. We'll go, I ran out of space there, so we'll just go with that. Now we're going to punch this into our calculator. We're going to use the normal CDF again. What's our low limit? 79.5. What's our high limit? 80.5. What's our mean? 93. What's our standard deviation? 2.55, is that right? Yes, no, maybe? You don't know? That's right. We punch all that in the calculator. What's the area of this space right here then? And that's the probability. What we're saying is, what's the probability that we do this survey of 100 people and we get exactly 80 people who say yes, they use the internet? That's what we're looking at here.
You know how you make different versions of the test? How is everyone on number 10 the same?
Because I didn't make different versions of the test.
Oh, I just thought it was
6 zeros.
6 zeros? That's why I put them on there. So you got 6 zeros and what? 415. So is it a very good chance that we're going to have 100 people and get exactly 80 to say? It's a very, very small chance. Very small chance. Want me to do the other parts also?
Yeah.
Part B, let me try to squeeze them in here. This time we want greater than or equal to 80. So we don't want exactly 80. We want the stuff that starts here and goes that way. So we want probability that X bar is greater than or equal to 80. So when we're looking at our normal curve, if we're on this same curve right here, instead of starting right at 80, we want everything 80 and over. So we're actually going to have to go down here and start at what? So we're going to tell the calculator, hey, we want everything from 79.5 and up. What do we know about that area over there? Give me an estimate before we start to plug it into the calculator. Should be 50%, more than 50, less than 50, a lot more than 50, a lot less than 50.
Pretty good amount more.
This should be quite a bit, right? So I'm guessing it's, 90-some% problem. When we punch it into our calculator, what's our low limit this time? 79.5, what's our high limit?
10,000.
10,000. Now on this, since we're only surveying 100 people, what could our high limit be? 100. We could put in 100 there instead of 10,000, because we're only going out to 100 anyway. But if we put in 10,000, we make sure it gets everybody. Our mean stays the same, our standard deviation. Zach, what'd you get for that one? 0.99. What's the next number after it?
Just more nines.
4 nines?
Just more nines.
All more nines?
Until like the last three, which is 401.
So is it gonna be pretty close to one hole? Yeah. So this one's gonna be really close to one hole. The other one, on the part C, we could have just, on part C it says the stuff less than that. So we could have just taken the number we got here and subtracted from 1. Let's punch it in a calculator instead. If we're going from there down, then our low limit's gonna be negative 10,000. Our high limit is 79.5. Our mean is 93, and our standard deviation is 2.55. Punch that into your calculator and see what you come up with. No, okay, I liked you better when you were typing, because you weren't talking.
I can go back to it.
That's fine, go right ahead.
I'm done.
5.99, but with the E -8.
So 5.99 e to the -8, what's that telling us? Tell me how to write that out. If we got e to the -8, that means we're gonna move the decimal 8 places, so how many zeros? 7. So what's the chance that when we're picking these samples of 100 people, that we get a sample that's less than 80?
Very low.
Very, very small.
Very, very rare.
We're not gonna get hardly any samples. We should probably never get a sample where less than 80 people say they use the internet. Other questions? Main thing on this test that I knew that a lot of you were gonna mess up is knowing when to use what. All right, and that's why I went completely over, and the test was almost the same as the review packet, and I went completely over it to show you, hey, this is when you are doing the binomial stuff, this is when you're doing the other stuff.
Ooh, that was so good. No, it didn't, it hurt.
All right, well, we're gonna cover today. Go ahead and start copying this down, take right notes.
So it might be I haven't played with Myers, but okay, whatever.
Again, this is sort of along the same lines as the last chapter, except this might be a little more useful because it's saying when you don't know what the mean should be, and you don't know the population mean, can we come up with some idea of a range where things should fall?
Yes.
And as we do this, as we go through this chapter, a lot of this is what you use in like the business world. So where should this fall at? Where should these different things work at? Last time I went to, before they started having the seniors go on, where they take you guys to that,
Manufacturing day.
to the manufacturing day, sorry, thank you. Last time I went, did I already tell this story? Last time I went, when they were still taking the sophomores, which might have been you guys. I don't know, did you guys go twice?
No.
It must have been last year's seniors then.
I think so.
When they took the sophomores, we went to, I think it was the place down in Lewisburg.
Lewisburg container,
No, it wasn't Container.
Pratt,
Might have been. What do they make down there? You
That's
know?
what we
Parker.
boxes.
Huh?
Parker,
No, it wasn't.
Parker.
You don't know.
It was one of the places they make like car parts and then they make metal stuff. So,
Not Lewisburg.
Literally,
Not
those are
Lewisburg.
the only 3 places in Lewisburg.
it might be right outside of Eaton. What's the place?
Eaton?
On,
Eaton?
on
So
35.
thanks.
On 35.
Neat.
Penny Penny?
They make fries.
Yeah, they make.
No, on the other end, on the other end of Eaton. Maybe they didn't take you guys to this.
The other end of Eaton,
Neat.
Going out towards, no, it's not Eaton.
like if you were
No,
gonna
on
go,
35.
if you were gonna go to like
That is-
Camden,
No, that's 7 or,
That's 120.
yeah.
no.
No,
35 is going towards, west.
West
Oh,
Oak.
Yeah.
There's a, so they didn't take you this one, I don't guess.
On 35.
What do you?
Do you know, like,
It's-
the
it's-
New Hope Road?
I
The
live
New
that
Hope
way.
Road.
You
It
do?
goes all the way.
I know. I don't know what's over there.
So there's a road that goes back, right before you get to the fairground entrance on that side of town that nobody ever knows
Yeah.
about. There's a road that goes back in there.
Like towards, that Silfex is down that way.
That
Or
Silfex
Meaton.
wasn't
It's
there?
like Silfex and then Meaton's on like the opposite side of
The
it.
Silfex wasn't there yet, I don't think.
So it
I'm
probably
pretty sure my
Meaton.
sister used to
Oh,
Meaton?
it was
No.
No, you're on the wrong end of town. The-
Bowling.
There you go.
Is it Bowling?
Oh
That's not on
my
35, that's
God.
on Motorola.
No, but it used to be bowling right there.
No, maybe it's not.
No,
It's not
Bowling's
Bowling,
not
because
there.
Bowling's off of.
It's
Bowling's the one that's back off the railroad tracks there, isn't it?
Off of 35.
Yeah, that's not it.
See,
You guys
take
are
that
on the
into
wrong
my
end.
house.
You guys are on the wrong end of town.
Okay, well, I know where you're at. You're at Silfex and me.
Everybody else apparently doesn't know. So you got 35. It comes up and it does this,
Yes.
right? You guys are over here,
Yeah, that's okay.
heading like down towards trail here. I'm on the other end of town.
Are you past?
Clear.
Draw some landmarks.
Outside of town,
You know
there's,
where- you know
there's
where
a
Mark-
fair, listen, there's a fair entrance out here
Yes.
that nobody ever uses.
Oh, yeah.
Oh, I know what.
All right.
I know what you're.
Like the one if you were to go into.
Then here, there's a place that sells like golf carts and stuff, and I don't even know if it's still there anymore. All these places have shut down, so there ain't really any landmarks there anymore. Used to be a gas station, all this stuff used to be
Yeah.
here, it's all shut down
It's a
now.
gas station, still just not.
Yeah,
Right,
I don't
it's
think
not
open.
used. There's an entrance here that goes back, and it's like, not real far back in there, but it's far enough back in there
There's a building right there.
that you can't see it. And there's a whole bunch of buildings right in here. All right, and one of those is a plant, and maybe they might use 2 of the buildings. And they make like car parts and metal stuff, where they form and fabricate different kinds of metals.
We didn't go there.
I
Right,
don't
did you
even
go there?
know what
But
it.
that's the second Eaton plant. I think there's 2 Eatons.
I'm
See, I don't
pretty
think, I don't think it's Neaton. I know it's not called Neaton.
The only thing closest to like the whole metal fusing thing would have been Sulfex because they use like sharpness and stuff. But
Right.
other than
Google
that-
Maps this.
See, and that's, I remember that place because they have a lot of, the newer equipment,
I
where
know,
they
like, where
can
you're
form
at,
all the
but
stuff.
I don't think I've ever seen it.
Right, it's back in there, so if you don't know it's there, you probably would never know it was there. Cause it's back in there. I know I used to go and there was,
So it's before the fairgrounds?
I think so.
Katie,
Yeah, I don't
like the
go
back
to-
way
so-
into the fair.
Yeah.
Like over
Like
by.
if you were to go to like,
Right, if you're on 35 going towards West Alexandria,
Yeah.
on the right is
Yeah.
the back entrance. It's over there.
I don't.
There used to be just semi-trailers back in there. And they sold stuff out of those semi-trailers. They sold like lumber and house, different house things like
How long
seconds.
ago?
That's been a while.
It
But,
kinda
but
does
this
seem-
factory I know is still there.
Was the gas station up and running?
Well, I mean, at some point, yeah.
2009.
Yeah, cause I've never
Not-
seen that gas station running.
No, that guy, not when we went there, no.
I mean, there's like car places everywhere.
But anyway, we went there, and this is the kind of stuff that they use. And I actually stopped and talked to one of the guys that was working, because next to him, he had this great big box that stood about almost 6 foot tall, and it was heaped full of these parts that he was making. All right, I can't remember what part it was. It was like some kind of bracket to hold something or something. But it almost looked like a rod for a car. It was something like where it was metal, and it had a hole in it here, but it was all solid metal. And they were making these. The machine that he worked on produced those. Well, when they produced those, like I said, it was a bracket, and it had little screw holes in it. And those little screw holes had to be a certain precision. And this hole had to be a certain diameter. So every so often, you'd see him get up with he had a little tool, and they had it set where he wanted it. They had a couple of them. And he had it set where he wanted it, and he'd take that little tool and he would grab one of the pieces off of the machine that just got made, and he would measure this, and then he would measure the distance between those screw holes, those bolt holes. All right? What's it called?
You don't have a name, it's Industrial Drive.
Yeah, it's Industrial Drive that's the name of the road.
Yeah.
But, so he would measure those. And like I said, he had this great big, almost 6 foot tall box sitting there next to him, and it was full of them. And they were just thrown in there, and all the rest of them, he was have to get off the machine and stack real nice and neat and put a piece of, like foam over it, so it wouldn't get dinged up and knocked, then do the next one, then do the next one, and sit there, do all this, then he'd have to run back and measure a few of them, and every so often he had to do that. And after everybody else walked away, I stopped and asked him, I said, what's going on with this box here? Why do you have this box of all these? And he said, well, somebody last night on the third shift wasn't paying attention and wasn't calibrating everything, and the machine got off, and these two holes right here were about 1/8 inch farther apart than they were supposed to be. And then that means when you go to put that, it was, like I said, it was some kind of bracket to hold something. When you go to replace that on whatever machine it is that you're replacing it on, a tractor or car or whatever it is, if those two bolt holes are off, they're not gonna line up with the existing bolt holes,
You won't be able to.
you can't use it. So they had to throw away, this box was about 3 or 4 foot wide, 3 or 4 foot deep, and almost 6 foot tall. And these pieces were probably, they might have took up about as much space as my cup. And it was full of them. They were heaping over the top. And it was because whoever was working third shift didn't bother to check things close enough and stop the machine. They just kept letting it produce. And the bad thing was that this was, what they make stuff out of was pressed metal.
Ooh. Wonder if he got wrote up.
Yeah, he got fired.
Yeah.
And you can't reuse press metal. It's not like it's
Recycle.
something that you could stick back in the machine and melt back down. So all this was just gonna be thrown out. And that's sort of what we're gonna do this chapter. Some of what we're gonna do is we're gonna figure out if we need these holes to be 1 inch apart, what can we actually allow to happen? How far off can the machine, because even though we want them to be 1 inch apart, does that mean that every piece that comes out is going to have those holes exactly 1 inch apart? It's not going to work that way. Something's always going to be just a little bit off. There's no real way to get exact. So we want to find a range here that we can be within. We can be within this certain range and still be okay. And that's what this chapter is about. So if you see stuff where I think last chapter we used M&Ms, same idea here. With M&Ms, they'll put a weight on a bag, and the M&Ms are never exactly that weight. All right? They're usually a little off one way or the other, but they have to be within a certain distance from what they should say. All right, well, we're going to start with a point of estimate. Point of estimate, and we're going to start with means, so we're going to use means. Point of estimate of a mean. We're also going to talk about standard deviation and variance. And this time, where I've been saying all year long that variance, not the most important thing. Variance, with stuff like I was just talking about with that, is what we want. How much variance can we have? Now variance is going to be a little more important. But first we're going to deal with the mean. All a point of estimate is, you'll hear point of estimate throughout this chapter. All point of estimate is that single value that we want to estimate about the population. So it could be the mean, could be the variance, could be the standard deviation, could be any of those things. The most unbiased point of estimate is the mean, is the X bar. And all that's telling us is, just like we said last chapter, the mean of the sample is going to be the closest to the mean of the population. Those are going to be real close. Variance and standard deviation might not look so close to each other for a population and for a sample. Glad I don't have to explain to you guys driving directions to anywhere. It'd take like 6 hours to get you guys anywhere.
No, I got you.
See, I'm only confused because I don't
Well,
know
he said back
anything.
entrance.
I don't know anything.
Pretty obvious.
Well, I know where the back fairground is, but my thought is I don't know anything that's over there. That's why I was like,
Validity of estimate is increased if the sample statistic is unbiased. Sample statistic has a low variability. All this means, the bigger N we have, the bigger sample size we have, the better off we are. And we should already know that. The bigger our sample is, the better chance we got of getting close to where we want to be. There's a better chance we have of getting a good estimate. So if we're dealing with M&Ms and we take 2 bags of M&Ms and we weigh them, we could be way off of what they're saying they should be. If we take 200 bags of M&Ms and weigh each one of those, then we should be getting closer and closer to where we want to be.
See, I'm one of those people, if I don't find out what it is, it like bothers me for like the rest of the day.
Good.
It's probably like Twin Valley something, because literally anything over there is called that.
Not anymore. Changed the tractor place. It's not Twin Valley anymore.
Not a shame.
I'll tell you what it is here in a minute.
Next time I drive by there, I'm gonna really look.
I'm telling you, you can't see it.
See, I feel like it has to be after the fairgrounds, though. After the entrance, like if you're going towards West Valley, I feel like it has to be after.
It might be. I don't think so, though. I think it's before.
Because if it's before it, well, but before it's like homes and stuff, I think.
All right, on this, finding a point of estimate. This is pretty easy. All we're going to do to find our point of estimate is, for the population mean, is we're going to find the mean of all this. And you know how to find mean. How do we find mean of this whole set of numbers? Add them up, divide by how many of them there are. So we just add them all up, divide by how many there are. Somebody help me out. I've already done all the addition for you, and there was 40 of them. What's that give us? 5232 divided by 40. 100 and what? 0.8. Now, if we go back to what it says the social networking website allows its users to add friends, send messages, and update their personal profiles. The following represents a random sample of friends for 40 users. Find the point of estimate of the population mean. So we're looking at how many friends. This would probably be a high estimate, but that might be for Mr. Eversole. And then Sydney's such a nice young lady. Hers is probably something like that, right, Sydney? These are just 51 probably people who felt sorry for me. And Mr. Eversole doesn't have any friends. I'm going to befriend you. So we're saying that the average person on that network has about 138 or 130.8 friends. Somewhere close to that, about 130.8. Again, all we're doing there is finding the mean. Adding them all up, adding up all the x's, divide by how many of them there are. So that's our point of estimate. Our point of estimate is we should be somewhere close to 130, 131, somewhere in that range. That's what we're estimating stuff at. Same idea on this stuff. Market researchers use the number of sentences per advertisement as a measurement of readability for magazine advertisements. In other words, what's that telling us? If you write some big long 6-page article and put it in a magazine, is it going to get read? Probably not. It'll get read by those people who are very, very, very interested in that one certain topic, and everybody else is going to look at it and skip over it. All right? So, you measure this, they're measuring this, and they're saying, okay, we want to keep it within a certain number of sentences, a certain number of whatever, so that somebody will actually read it. And you notice down here we have all these. If we want to find the mean of that, again, we'd add all those up. Add them all up, divide by how many of them there are. 620 divided by 50, we get 12.4. That's our mean of our sample. That's our point of estimate. So the average for our sample, the average was 12.4 sentences. Nothing hard about that. This is where it starts to get a little more difficult. This is where we're actually adding in something new. I want you to know too that if you thought that last test was hard, is it going to get any easier? I hope. Absolutely not. If you're not paying attention, I'm telling you, you're going to be lost.
I just want to hear it.
Next week, I can make a review in there.
Okay, Katie, I'll plan to do.
And then I'm probably not ready to send it.
Yeah, so definitely don't do that. Build your house.
Did you say we're building my house?
Yeah. That sounds like a deal. Said house, not plural.
Said house, not plural.
You can live with them. I mean, if you don't love with that, you can live with them.
What are you going to call it?
I feel like you'll have bulls or
Football.
all bulls.
You don't know what you want to major?
Football. What's the next one?
All
freak car.
What's what?
What's in red? I think I don't know. I got
I'm
talking about the word. Associate's degree.
Interval estimate.
What is it?
Interval estimate.
Also, I was basketball.
You're what?
I'm not just saying, that's red.
Oh, yeah.
Give me a bowling.
I'm so bad at bowling.
It's pretty sweet for you too.
Yeah, I mean, basically, you're on the athletic.
So the probability that mu is exactly 12.4 on that last example is almost zero. We find our point of estimate, that's the mean of the sample. Very unlikely that the mean of the population is that exact thing. All right? But it's more unlikely that it's going to be within a certain range of that number that we found, our point of estimate. And that's what this is doing. We draw a number line and we say, we draw a number line here and we say, okay, we put 12.4 right in the middle. And we go out each way, so many numbers. And this time it's not just 3 standard deviations. We could go out, a whole bunch. But we're going to look at what's the probability that the mean of the population falls between some certain range, that we need it to fall in between there. So we might say, what's the probability that falls, I think on mine here, I said, what's the probability that the actual mean of the population is going to fall in this range from here to there between 11 and 14. Looks like I went a little higher, a little lower than 11, and a little higher than 14, but something like that. So we're looking at what's the chances that it falls in there. And that's how confident we're going to be that we're close to the mean. So what we're going to build is we're going to build a confidence interval. We're going to be able to say that we're 50% confident that the mean of our population falls within this range. All right? Or we're going to be 90% confident, or we're going to be 95% confident, or we're going to be 75% confident that it falls in this certain range. That's what we're looking at. before I go on. Does that sort of make sense? So what we're gonna do is we're gonna have this 12.4, that's our point of estimate, that's gonna go right in the middle. And then we're gonna find some number down here, some number up here, and we're gonna say, hey, we're 95% confident that the mean of the population is gonna fall in there somewhere, every single time. Now, the wider we make it, if we went to from 100 to 10,000, then we should be able to say with confidence that, what percentage of confidence can we say that the mean's gonna fall in between there and there?
All of it.
100%, right? Well, we don't want that. That's sort of dumb. That's like with my part that I was talking about up here. You know, you could say, okay, we want it to be an inch, but so that it's less work on the guy running the machine. Let's say we say it could be from an inch to down to no inches, so it could be right next to each other, or it could go up to 5 inches. Well, that's not going to work. So we want a range here that actually makes sense for what we're doing. Point of estimate goes in the middle. You add or subtract the margin of error. Margin of error, that's the next thing we're going to find here in a minute. Margin of error. How much error do we actually want? Again, make sure you can find this. If not, I have a few other copies up there. But make sure you can find this, because on the bottom of this, it's got critical values and it's got this stuff over here. We're going to be using that.
Is that the one that we just used?
We used it. We had it last chapter, yeah. I passed out last chapter. You can't find it. You can grab one, not right now, but after we get done.
Might catch some surface out. There's 7 or 7:30.
On this one, if our point of estimate is 130.8, I don't know if I got, no,
They're good.
previous. 130.8, we would put it right in the middle here. And our margin of error is 15.7. So we're going to come out this way, 15.7. And we're going to go over this way, 15.7. That's going to be our confidence interval. Mine doesn't look very good. I went too far one way, not far enough the other. But that's going to be our confidence interval. This should be right in the middle. And then we're going to be a certain percentage confident that it's going to fall, the mean's going to fall within that range. So all you're going to do to find this confidence interval, I think that's on the next slide, but you're going to take that, you're going to take your point of estimate, subtract off the margin of error, and then add on the margin of error, and that's going to give you the two ends, how far out you're going to go. Before finding the margin of error, you must decide how confident you want to be, how confident you need to be, maybe. Level of confidence. Level of confidence, the letter we use for level of confidence is C. So on the next vocab or symbols test, when I put C on there, what are you going to write down? Level of confidence. The probability that the population parameter is in the interval, the ones that we use, most of the time, 90, 95, and 99. If you have that chart, and actually the chart has 80 on it also. Level of confidence, it's got 80%, 90%, 95%, 99%. And it gives you z-scores that go along with that. So you don't have to stop and find the z-score every time. It gives you the z-score, and you can just use it. something, but.
Is that phone book? Shit.
Dang, it's been a minute since I seen one of those.
Yeah, I didn't know they still like gave people those, but one day I was like working, no they do. One day I was working at, the Walmart Subway and some man came in and gave it to me and he's like, cause I guess they give them to businesses or something. I don't know, I was like, what is this? So
I
weird.
remember like fourth grade when I had to use this.
You would use it, why?
Like to call my grandma's name or number. I looked up her name.
Why is it so small?
There's a lot of them.
It's just purple county.
Didn't it used to be like really big? I remember phone books, weren't they like that big?
I would like to take phone books and try to call my friends.
Alright, so these are, especially if you can't find that chart, you probably want to write this down. Those are what they tell you.
What chart is it? What's the name of it? I think I have a chart right here.
Standard normal distribution.
What's the max? Got it.
So this tells you, if you look at the bottom of that chart, if you have it, it just tells you at 90%, these are the Z-scores we want to be at. 95%, we want to be at this Z-score. 99, we want to be at that. And these are usually plus or minus. All right, they're usually plus or minus. So we're saying on our normal thing, if we want 90% of the data to be within a certain Z-score, if we want 90% in here, then we're going from negative 1.645 up to positive 1.645 on the Z-chart. That's all that's saying. And down here, negative Z, C, so that's your critical values. This is going to be your confidence interval when you put those two together. These are called critical values. Your Z-score here, if we want to be 90%, it's going to be negative 1.645, positive 1.645. So critical values, you're looking for these two critical values. That's what we're going to be looking for a lot of times. Sometimes we'll want them, well, usually we won't want them as Z-scores because you could just look that up on the chart. We'll want them as raw scores. How far can it be off of that? How far can our two holes be apart from here to there? It's got to be within a certain range. Values that separate the sample statistics that are probable from those that are improbable. So these are our critical values. This stuff out here should not be happening. Stuff in here is what we want to happen. We want it to be in that range. Those are called your critical values again, same as the last slide. Level of confidence, C. The probability that the interval estimate contains the population parameter. That's your level of confidence. We want to go, if we're here, whatever our Z's are, we could be at 90%, 80%, 95%, 99%. We want 99% of the stuff. Because even though if we're making that part, that bracket that I was talking about, even though we're real careful and we keep calibrating the machine and keep everything, keep on top of it, keep measuring everything, is every single part always going to be 100% perfect? No. So that's why we go up to 99. Most companies, that's what they want. They want 99% of the stuff that they put out to go out usable.
Was it Timken Steel?
That sounds right.
I think that's it.
What the heck?
Something still.
No, it's off of 35.
There's
but
one in
it's
here
the
also.
Industrial Drive. Yep, and
Yep.
Yep.
But I think it's after.
So, listen closely to this, because on this is something you're going to have to do. If you want, when we're looking at, let's say we're looking at 90%. Change that to 90%. We want 90% of the data to fall in that range. What percent of the data is going to be in this part out here?
20.
Why not 10? Because you got the other side. So there's going to be 5% out here, 5% over here. So that's why it's saying take half of it. You take 1 minus your confidence level that you want, 1 minus the 90% or 1 minus 0.9, and then you take half of that. If we were at 99%, then this would be like 0.05%, all right? Because we want to be at 99% confident. The level of confidence is 90%, means 90% confident that the interval contains the population mean. So if we're at that, it's going to 5%'s out there, like we just said. These z-scores, if we're on our z stuff, always going to be negative 1.645 and positive 1.645. Important to know that, important to be able to find it on that chart, because then you don't have to find the z-scores manually. You don't have to do it mathematically yourself. If we wanted to be at 99%, then that means 0.005 out here, or 0.5%, is going to be this area out here. Don't look at my graph because I didn't change the graph when I did this. Those z-scores, plus or minus 2.575. So this z-score would be a negative 2.575. This one would be a positive 2.7575. Sampling error. This is important. How to find this sampling error. Sampling error is the difference between the point estimate and the actual population parameter value. So in our case, what we're doing today, the point estimate is the X bar, and the population parameter is the actual mean of the entire population. So it would just be X bar minus mean is the sampling error. Mean is generally unknown. Most populations we can't actually find the mean. We've talked about that all year long. And the X bar varies from sample to sample. So if Ms. Clark takes one sample and Lucas takes another sample, their X bars are probably going to be different from each other. All right? But what we're trying to say is, yeah, their X bars are different, and if we had everybody in the class, everybody's would probably be different. They should all be within a certain range of the actual mean of the population. Margin of error. To find the margin of error, we use this formula right here. That's probably what we're going to use most of the time. E stands for margin of error. Make sure you know that. Another one, probably put on the next vocab test, symbols test. E is margin of error. Notice standard error, that's what we talked about last chapter. It's just sigma divided by the square root of n, so we're still using that. I told you earlier when we were doing that problem off the test, we'd still be using that. All we're doing is taking the z, the critical value, times that's standard error that we talked about, or that, standard error that we talked about last chapter. This works well when your sample size is larger than 30. Actually, it only works when your sample size is larger than 30. 30 or larger, I should say. What happens as the sample size gets bigger? It's better and better, all right? So the bigger sample we can take, the better off we are. But we need at least 30 every time. Sometimes called, this is also sometimes called the maximum error. So that's the maximum error that we want. We don't want to be any farther off than that. It's also sometimes called tolerance error. How much can we be off? How much can we tolerate? If we use that magazine one, assume that the sample standard deviation is about 0.5. They'll usually tell you the sample standard deviation. Sometimes they will, sometimes they won't. Sometimes you may have to use your calculator to find the standard deviation. This time they tell us. So if we want to be, let's go back for a second. Hit the wrong thing. Hit the wrong thing again. We want to be 95% confident that our mean falls in this range that we're going to come up with. And the actual population has a 5.0 standard deviation. So if we want 95% confidence, and that means this area out here and this area out here, we want to be 0.025, so 2.5% on each end. 100 minus 95 gives you 5, divide that by 2. That's your area on each end. That gives us 95% of the area in here. So we're saying we want to be from right here to right there. We want this many sentences to that many sentences. If we're using 95% confident, then that means these z-scores are negative 1.96 and positive 1.96. And we're finding those areas in between. Again, you could use the chart. I'm not going to use the chart so much on here, but we could use these charts to help us with some of this. 95% of the area falls on that. You can approximate the distribution of the sample means with a normal curve by using the central limit theorem, since our sample was larger than 30. We take this error, we find the error. Key idea here. A lot of times we won't know the error of the the standard deviation of the population. If we know the standard deviation of the sample, then we just use that. Use S if don't know sigma. You don't know this population standard deviation, then you just use S. We come up with 1.4 when we do all that math. Remember, this is our critical value. That's our z-score. Error of the population, or standard deviation of the population. That's N. 95% confident that the margin of error is about 1.4. So that's our margin of error. Let's go back for a second, because I'm going to stop right here. So if we're going to make a confidence interval for that, anybody remember what was it? 12.8? Was it 12.8? The number of sentences, I think, was the mean. Does anybody remember what was the mean for the number of sentences? Was it 12.4? That sounds right. 12.4. If this is our margin of error, what we want to do to find our interval, what we're sure that the mean has to be between, is we're going to take that 12.4 and we're going to subtract 1.4. So we're down here to 11.0, and we're gonna take that 12.4 and we're gonna add 1.4. So we're up here at 13.8. So what we're saying is, if we took a sample of 50 magazine articles and we found the mean of those 50, or actually, if we took all the magazine articles in the world and we found the mean of them, we're 95% confident that we would fall in the range of 11.0 up to 13.8 sentences. We're 95% confident that the mean of all the articles in the world that are in magazines is going to fall in that range. Seems sort of useless. Who cares about sentences in a magazine? But same idea for all the other stuff that we're going to do. So this right here, you might want to jot that down real quick. That's all you're doing. This side, you're subtracting the sample mean minus your margin of error. On this side, sample mean plus margin of error. That's how you're finding your confidence interval. How far from here to here. And this you've already written down. That's your margin of error, how to find the margin of error. That's your assignment. What we'll do with this is next class we'll go over some more of this and we're going to add on to that. But try some of it so you can sort of get an idea of what you're doing. You all right on that? All right, well. You don't want to mess